In the last section we talked about secant lines and tangent lines, and we learned to approximate the slope of a tangent line using secant lines with very, very small intervals in the denominator for time between 2 points. We're going to take that idea and work further toward limits. Basically with limits we're looking at how do the values of a function and the function that we're going to talk about in general, we'll call f of x. So how do the values of the function f of x behave when x approaches some value c? Now the notation that we use for x approaches a number c, we use x and then we use this arrow approaches a number c. So x approaches a number c. And we want to know what's going on, whether or not f of c, meaning if I took c and plugged it into the function itself, is defined. Meaning, is it a hollow point, is it a solid point, doesn't matter. So that's one of the things that we want to look at. Another thing we can talk about with limits is we're really looking to figure out what do the y values do when x approaches c, this constant value. Now, what we're thinking about here when we're talking about the y values is our functional value. Now all of this will make a lot more sense once we start looking at some graphs and some actual functions, but there's 3 ways that we can determine limits. Now we don't always like to do all 3 ways, because once we find one solution we're usually good with that, but if one way doesn't work I could switch to another. But basically I can find limits numerically, graphically, and analytically, or algebraically is another way to say that. And so we're going to be using all 3 of these different methods based on some different types of examples. I really like to use Graphical to get kind of started with introducing the idea of limits. So let's get started looking at a graph. When we talk about a limit and I look at a graph, this value of c that we're talking about, let's say, is right here. And then this value down here on the graph where I plug c in is f of c over here. So if I wanted to know what is the limit as x approaches c, I would have to first of all approach it from the left, and that's what this negative sign means. It's a superscript. I would also have to approach x from the right. X approaches c from the right of the function. And if both of these are the same value, then what ends up happening is that's the solution to my limit. So looking at this picture that I have, approaching from the right means moving in from the right. So over here is the limit as x approaches c from the right. And f of x is my function. So we can see as we approach c from the right, our value is some f of c. It's whatever this y value is. Now as we approach c from the left, so here I am approaching c from the left, and that's that little negative value, means from the left, I can see that I eventually get to that same value of f of c. So this one, as I approach from the left, is f of c as well. Now because these are equal, and these have to be equal in order for the limit to exist, the limit as x approaches c is f of c. They agree. So if these values are equal, the overall limit is the same as these values. So that's the idea of a limit with a nice kind of straightforward function. Now this can change. What if we have asymptotic lines? What would this look like? So let's look at a graph where we might have some asymptotes. Now again, an asymptote basically means a line, a vertical line on the graph, in this case, where the value approaches and gets really, really close to it but never quite equals that value. So we'll just plug in this little bit of a graph. So this is my value. We'll call this A this time instead of C, just to make sure you realize it's a different point on the graph. So what I do is I look at the limit as x approaches A from the left. I look at the limit as x approaches a from the right, and this is the function f of x again. So this graph, this line is f of x. Now, as I approach from the right, and I follow this line up, this is the limit as x approaches a from the right, I can see that this is going off toward infinity. Okay, let's look over here. As I approach a from the left, I can see that this is also going off toward infinity. Now, if I get a limit that's infinity, what that's saying is there actually is no limit because there is no bounded value here for that graph. So this limit basically does not exist, and we'll talk about what that means here in a little bit. These are equal, however. So this tells me that the overall limit as x approaches a of my function f of x is equal to this infinite value. It's agreeing from the right and from the left. However, because infinity is no bound, meaning it's not a limiting value, if you could say, you know, the speed limit was infinity, there's no limit then. Therefore, I would have to say here, the limit does not exist. And we say this a lot, the limit does not exist. And we have an abbreviation for this, and it's DNE, does not exist. So if I wanted to, on these limits, I could have said DNE, DNE. But once I find one limit that doesn't exist, that means the overall limit can't exist either. However, I like to go through this. There's different reasons why limits can't exist, and this is only one of them. The limits agree at infinity, so that's information that's useful, but that also implies the overall limit doesn't exist. So I like to include that part in the conversation. Let's go ahead and look at another graph. For this graph, let's go ahead and put in our asymptotic line at B. And for this graph, we have approaching from the right, and we'll look at it approaching from the left. So I'm looking at the limit as, whoops, x approaches b from the left, and we'll call this function g of x this time. Limit as x approaches b from the right of g of x. And I compare these. So if you look at this, as I approach, whoops, as I approach from the right to get started here, here we are. As I approach from the right to get started here, I can see this is the limit as x approaches b from the right. I can see that that's going toward infinity. It's going off toward infinity. Now, as I approach b from the left, I can see that this is going down toward negative infinity. So these definitely do not agree. So these are not equal. Therefore, the limit as x approaches b of g of x does not exist. So you can see they didn't exist for two different reasons. Up here, the limit didn't exist because they were bound by infinity. They agreed, but were bound by infinity, or unbound by infinity. Over here, they didn't agree, and so that's why the limit doesn't exist. So I think it's important to have a good distinction between those two reasons why a limit could exist or not exist. Let's go ahead and look at another example, and we'll be looking at some graphing here. So if you have your graphing calculator, it might be helpful to get that out. We're going to look at this limit a couple different ways. So for this example, I'm going to look at the limit as x approaches 0 of the sine of x over x. Now you might be tempted to cancel these x's, but you can't because the x in the numerator is part of the sine function. And I really am picky about always putting your trig functions, the arguments of your trig functions, in parentheses. So please get in that habit, especially when I'm grading your handwritten homework and your exams. I want to be really clear on to what that means. Now when we typically evaluate a limit, the first thing we do is we just plug directly in to see what happens, because if we can plug in and get an answer, that's really the best case scenario. So this would be the sine of 0 over 0. We know from the unit circle that the sine of 0 is equal to 0. 0 over 0 And in terms of a limit, that's called indeterminate. You might say, well, wait a minute, 0 in the denominator is undefined, but that's if we're looking at things just using arithmetic. We're talking about the limit, the behavior of a function here. So 0 over 0 is a special form. It's called indeterminate. And what it means when you get something that's indeterminate, you have to do more work. You have to figure out what's going on here with this particular limit. So the other work that I could do here is graphing, or I could also look at this numerically. So I want to look at this graphically first. Okay, so in order to draw this graph, it's not just a nice little sine function or something like that that we could probably sketch out on our own when we got to a test or a quiz. And you should know how to sketch your basic functions of sine, cosine, tangent. The other ones are a little bit harder, but the basic functions you should know, and definitely know the unit circle as well. So let's go ahead and graph this one. Let's graph sine x. And if your calculator doesn't have that fraction function, just make sure you put everything in parentheses. So we'd go sine x in my numerator over x. And let's go ahead and have a look at what this graph looks like. Now we might have to change our graph a little bit. We might have to change our window. Right now it just looks like a straight line. There's a lot more going on here though. If we change our window, we'll see what it is. For our, I like -10. Let's go +10 on my x. But my y-axis, I'm really going to need to shrink things down here. Let's go -5 to 5. And a lot of times you just have to simply kind of work through here, changing your window settings until you can get a graph that looks reasonable. I'm going to change my scale here to just 1. And that graph probably could have gone a little higher up. Okay, so it looks like it's only going up to 1 here, so let me change that window again. I'm going to change this from -1 to 1 because I want to get a good picture of the graph. I don't want the whole screen to be blank. Okay, that looks like a good graph. Now if I could figure out some of these cross points, that would be good as well. But let's go ahead and snap this into our lecture. So this is the graph of the sine of x over x. Now we looked at our scale pretty carefully when we put this in. So we know that this is going to be equal to, on our axes, 1, 2, 3, 4, 5, 6. So this looks like to me where it crosses is probably pi because it's slightly more than 3, 3.14. So this looks like it's about pi. This would be -pi. Where it crosses again would be 2 pi. So you kind of get the idea. Now on our vertical axis, this is the number 1. Remember how we set our scale. So in order to figure out what's going on here, we're going to take the limit from the right and the limit from the left. And thankfully this graph agrees at that particular point. Now one thing this graph doesn't give us is the fact that there's a hollow point here. Okay, so we have to keep in mind there's a hollow point. Now the calculator doesn't know this unless we look at the table, but we have to be able to know that. So if we look at second table here and go to 0, you see right here as we have error across. So the calculator does know that from the table value, but it doesn't really know that from the graphing perspective because it's just playing dot to dot when it graphs. So remember, that is a hollow point. So let's go ahead and look at the limit as x approaches 0 from the left of the sine x over x. Remember, put parentheses around the arguments of your trig functions, please. And let's go ahead and approach 0 from the right of sine x over x. So as we approach from the right, we follow this graph. We can see that this is getting closer and closer to 1. It doesn't actually ever equal 1 because we have a hollow point, but the idea of a limit doesn't require that it's exactly equal. It just means that that's the behavior as we get closer to that point. So as we approach 0 from the right, I get 1. Let's go ahead and approach 0 from the left. So the limit as x approaches 0 from the left is also equal to 1. Now because these agree, because these are equal, That means the overall limit as x approaches 0 of sine x over x also equals 1. So again, I need that limit from the left to equal the limit from the right. Now, even though this is a hollow point, the limit doesn't require that it's a filled point. The limit just basically means what is the behavior of the function as it gets closer and closer to a particular value. Now, on a test, unless it's just a real basic sine, cosine, tangent graph, I wouldn't expect that you would know how to graph this. I would provide the graph and then you could answer questions about that, since you will not have access to a calculator, although you will have a note card. So let's do the same problem. This is the graphical approach that we have up here. Let's do the same example. The limit as x approaches 0 of sine x over x, and of course we know from above we plug 0 directly in. This was an indeterminate form. And indeterminate means to do more work, meaning I have to try another approach to this. We already showed this graphically, but I want to show this same using the numerical approach just so you can see and compare the outcome here. Now the outcomes will be the same no matter which approach you use, but you might get an idea as to which approach you like better. Now the numerical approach is calculator heavy, so if you have access to a calculator on your homework or quiz, that might be a good approach. On a test though, you won't, so it's a good idea to know more than one method. So here, if we look at this from the numerical perspective, basically what I need to do is I need to make a table. Now I also need to know something about x, and we're going to say that x is in radians, so let's keep that in mind as well. So I'm going to plug in some values of x, and then I'll get those values of x back out when I plug them in, and that'll give me some idea as to what's going on with this particular graph. Now I have to approach from the right and the left again. I can't just approach from one side. So what I want to know is I want to know what's going on at 0. And because I want to know what's going on at 0 and I approach from the left and the right, I need to choose some values above and below. So my values to the left of 0, I want to choose some things, let's say like negative 0.01, negative 0.001, negative 0.0001. So as you can see, I'm getting closer and closer to 0. Now we want to do the same thing on the right. I want to come in from the right at 0.01, get a little bit closer. I want to check out the behavior of this graph. And then these are my x values, and then down here this would be my value of sine x over x. So a couple things to note. X is in radians, so when you plug these into your calculator, make sure you're in radian mode. So as I plug in negative 0.01, I'll put in the values that I got when I plug these into my calculator, and I guess we could do one real quick. I don't want to fill out the whole table here. Okay, so we'd have the sine of negative 0.01 divided by, and again we need parentheses around the arguments of your trig function, negative 0.01. And I forgot to double check, but I'm pretty sure we're in radian mode. But we get 1, 2, 4 9s and an 8334. So I get 0.9999834. Now I'm going to do the same thing over and over again with all of these numbers, and then I'm going to start to see a trend here. Now we're going to run out of space to write all these 9s. Here's I have 1, 2, 3, 4, 5, 6 9s. 1, 2, 3, 4, 5, 6, and then an 8, 3. 1, 2, 3, 4, 5, 6. I think you'll get the idea here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 3, 4. And then from the right, it's really the same pattern. 8, 3, and then we have and then 0.001. tack an 8 on the end here. So now what I have is I approach this from the left, so the limit as x approaches 0 of sine x over x from the left, you can see that this is getting closer and closer and closer to 1. Now as I look at the limit from the other direction, the limit as x approaches 0 from the right of sine x over x, I also am getting closer and closer to 1. So because I'm agreeing at that value of 1 from the right and the left, that means my overall limit as x approaches 0 of sine x over x equals 1. So this table shows me that as well. It takes a little bit longer to plug in, but it really does give you exactly what's going on here. Now remember, if we plug 0 in, I get indeterminate. So I'm trying to figure out what this value is because I can't plug directly in. If you can plug directly in, that's always the easiest thing to do. Let's go ahead and look at some a little bit easier limits. For this limit, I'm going to be looking at a linear function. So I'm looking at the limit as x approaches 4 of negative 3x plus 10. Now the easiest thing to do right off the bat with any limit is to just plug directly in, if you can, and see if you get out a numerical response that's not infinity or indeterminate or undefined. So here I'd get a negative 12 plus 10, and that's equal to negative 2, and that's my solution here. It's no more complicated than that. Now let's go ahead and look at this graphically. Now if we looked at this graphically, this is a line. It has a y-intercept of 10, and it has a slope of negative 3. So we have a negative slope. And this point right here would be 10/3 on the x-axis. You can just set this equal to 0 and solve. So the question here is what's going on as x approaches 4? And it looks like I'm running out of space here at the bottom, so I might have to extend this out a little bit. 10/3 is about 3 1/3. So we'll say 4 is right about here. So as I'm approaching 4, I want to be able to, I just don't like this. I'm going to move this whole thing. I want you to be able to see how we approach from both sides. Maybe I'll just make it a little smaller. It's going to be the same graph. I just want to fit it on the screen so we can see where we approach from the right and from the left. So we're going to say this is 10. This looks better. This point is right here at 10/3. This is at the point 4. And this is the point on the graph then. So as we approach from the right, we can see that this limiting value is toward negative 2. As we approach from the left, we can see that this limiting value is 2 as well, or sorry, negative 2 as well. So this verifies graphically what's going on here with this limit as well. But if you can, the easiest thing to do is to plug directly in. Now one thing that we notice here is the limiting value and the functional value were the same. Now this isn't always the case. In the work that we did just up above with the sine x over x, that wasn't the case at all. It was undefined. It was a hollow point. The limiting value was equal to that hollow point, and that's okay. Let's go ahead and look at some more examples of what we could look at in terms of plugging directly in. And when we talk about plugging directly in, we're just basically looking at that analytically or algebraically, and then sometimes we have to work further to simplify. So let's go ahead and look at another example. So for this example, I want to look at the limit as x approaches 2 of 2x plus 3 over x minus 2. So again, the best thing to do is to plug directly in first and then see what happens. 4 plus 3 is 7. 7 over 0 is undefined. If this fraction is undefined, this is not indeterminate. Indeterminate means 0 over 0. If this is undefined, therefore the limit does not exist. I'm done. Now I'm kind of interested to know why it doesn't exist. Usually it has to do with an asymptote. This function is undefined at 2. So let's go ahead and graph this real quick. 2x plus 3 over x minus 2. So y equal, I'm going to put this one in parentheses just in case you don't have a fraction key on your calculator, so you can make sure you see how to do these. 2x plus 3 divided by x minus 2. So entire numerator and entire denominator in parentheses. I might have to rewrite this a little bit because I really can't see a lot of what's going on here. So let's go ahead and change our window. Negative 10 to 10 looks good. Let's go ahead and change my y min and my y max, negative 10 to 10. Now there's other ways to do this. Under the zoom button, I believe it is, or the window button, you can just go to like zoom square or something like that. I like to change these myself because I like to have a little bit more control over what's showing so I can adjust it. So this is a picture of that graph. Now, one thing that your calculator doesn't know is about asymptotic lines. It just tries to connect the points. It's not in there thinking about this, but we know that there's a vertical asymptote at x equal 2. So this is the vertical asymptote. And we can determine this by looking at the denominator. So really what I have here is I approach 2 from the right. I'm going toward infinity. As I approach 2 from the left, this is not going toward positive infinity, but it's going toward negative infinity. These don't agree, therefore the limit as x approaches 2 does not exist. So the reason why this limit does not exist is particularly because the limit from the right and the left don't agree and neither one of them are bounded. So just being able to say undefined up here, therefore DNE, I like to know a little bit more about what's going on. And we can look at this just because we know what the vertical asymptote is and then plug in a few values to get the idea if they're going toward positive or negative infinity. So I like a little more information on that. So when you're setting up your handwritten homework and your exams, keep this in mind. If you were to just slap in 7 over 0 is undefined, therefore the limit does not exist, that's correct, but if you want full credit for the problem, you might want to go into a little bit more of a conversation about this piece down here, particularly explaining which of the reasons why it doesn't exist holds true. Let's go ahead and look at another example. Knowing some of your basic graphs is going to be very important, and this next one is a basic graph that I would expect everyone to be able to graph without the use of a calculator. So for this one, let's look at the limit as x approaches 0 of 1 over x squared. Well, the first thing we do is plug directly in. 1 over 0 is undefined. Therefore, the limit does not exist. But I want to know more. I want to know, well, why? There's a couple different reasons why it couldn't exist. Well, from this problem, we can look at the x squared, and I can say this function is undefined when x is 0. So x equals 0 is the vertical asymptote. Now the graph of 1 over x squared lies in the first and the second quadrants. And again, this is a basic graph that I would expect that you would know. So we can see, as we start talking about the limit as x approaches 0 from the left and we talk about the limit as x approaches 0 from the right, we can see both of these are going toward infinity. From the right and from the left, they're both going toward infinity. Now these are equal, so the overall limit as x approaches 0, we can also say is infinity. But this is no limit at all. Infinity is not a limit, so I'd have to say then therefore the three dots and the shape of a triangle mean therefore. I keep writing that, but I don't know if I've ever explained what that means. So therefore, that's what that symbol means. The limit does not exist. So both of these limits didn't exist above in this one, but they didn't exist for a different reason. So I think it's really important that you distinguish between those two reasons. Now a lot of times we can look at things algebraically to see what's going on. And again, our first bet is to plug directly in and then kind of work from there. So if we can, plug in. If we get a nice answer, you're done. If you don't get a nice answer, you're going to have to attack this from a different view. Let's go ahead and look at the limit as x approaches -3 of 2x squared minus 18 all over x plus 3. Now right away I see I have a problem here. When I plug -3 into the denominator, I get a 0 back out. When I plug a -3 into the numerator, -3 times -3 is 9, times 2 is 18, minus 18 is 0. 0 over 0 is an indeterminate form. So if this is indeterminate, this means to do more work. I don't know the answer yet, so I'm going to have to go figure out what else I can do. Well, graphically, I suppose I could look at this. I've done that. We could look at this numerically, certainly plug numbers in. I want to look at this one algebraically. So algebraically, I'm going to look at this as the limit as x approaches -3 of the function. And I want to look at something here. I want to look at some restrictions. If I look at the restrictions, x can be anything I want except what makes the denominator equal to 0, or if I had radicals involved, I'd have to consider that. I just need to remember x cannot equal -3. So if I factor this, I get 2x squared minus 9. I'm going to keep working here. Don't ever drop your limit notation as you're working. Make sure you include that, drag it along, because a lot of times we do so much work at the end we forget what we were even up to begin with. Okay, so we can see here that I get this canceling to occur, which is really nice because this was the thing that was causing me trouble, was that denominator. So I'm left with the limit as x approaches -3. Yes, -3, I dropped that negative here, of 2 times the quantity x minus 3. So I could go ahead and just plug directly in now, and I get -12 here, and that's my limit. So basically I factored, and I went through this and factored, and once I factored I was able to evaluate the limit. And that's algebraic approach is usually a nice place to start. Again, there's the numerical and graphical approach as well, so I could graph this function. If you graph this, it would look like a straight line, and the computer or the calculator would forget to give it a hollow point, so you have to be careful about that when you use graphing. Last one we're going to look at here is a piecewise function. I really like looking at piecewise functions. So to get going on this one, I'm just going to make up a graph. I'll try and be pretty accurate here. We're going to have to be pretty specific because we don't have a function defining this. So everything I do will be based on what I can see on the graph. So the first part of my graph will look like this, and this will be a function. The next part of my graph, it's important that we see that this is a hollow point from here to here. And then let's say I have another hollow point here, and then let's go 1 unit to a filled. And then from this filled point, I'll go off to this hollow point, and then this continues on. So this is quite an interesting graph. There's a lot going on here. So it makes a difference whether I have filled or hollow points, not for a limit, but for my functional values. And this is going to get into the idea of continuity very quickly. So we need to be able to look at this in terms of hollow and filled point, and then also limits and functional values. Okay, so this is my piecewise function. There's a lot of interesting things going on here. So to get started, let's look at the limit as x approaches 0. I want to know what the limit is as x approaches 0. Well, for me to do this, I have to approach it from two directions. The limit as x approaches 0 from the left, limit as x approaches 0 from the right. So basically what I'm going to do is I'm going to follow this graph from the right and get closer and closer to 0, and then I have to jump up here, and you can see my limiting value is 4 from the right. So even though there's a hollow point, it means it gets closer and closer to 4 but never quite equals 4. Now as I approach 0 from the left, I'm going to start here in the bottom left, and you can see my limiting value is 0. These are not equal, therefore the limit does not exist. So this equals D and E, does not exist. So hollow points are important here. A lot of people think because there's a hollow point the limit can't exist, and it's really just the opposite. As I get closer and closer to a particular value, that can exist. Now I'm going to move these down just so I can always keep the picture in the view. So we'll still have this work underneath if I can get it to go. There we go. And then we'll come back up here so I have the graph always close by. Okay, let's go ahead and do another problem. Let's look at the limit as x approaches, let's do 2 this time, of f of x. So I'll approach 2 from the left, and I'll approach 2 from the right. Okay, so as I approach 2, let's do from the left this time. So here's 2, and as I approach it from the left, my limiting value is the same as my y value. You can see that that's equal to 3. Now as I approach 2 from the right, and I follow this through, you can see I'm also approaching that same limiting value, which is 3. These are equal, therefore the limit as x approaches 2 of f of x equals 3. Because the limit from the right and the limit from the left was the same. So my overall limit was equal to 3. So I'm going to again move this down because I want to do our next problem with the graph right next to it. Now for my next problem, so far everything has existed, I guess if you want to say that, but that doesn't always have to be the case. Sometimes the limit won't exist. Okay, so for part C here, let's look at the limit as x approaches, let's do 4 this time. So I'd look at the limit from the left, and I'd look at the limit from the right, and then compare. So as I approach 4, I'm getting closer and closer to the x value of 4 from the left. My limiting value is 4. You can see I'm getting closer and closer to this value of 4, but never actually quite reach it because of the hollow point. As I approach from the right, you can see that the limiting value is also 4. So even though that's a hollow point, that's okay. These are equal, so therefore the limit as x approaches 4 of f of x in this case would equal 4. So this would equal 4. So don't let the hollow points kind of obstruct your solutions here. A lot of times people get really hung up on whether you have hollow or filled points, and that's important when you're evaluating a function, but when you're evaluating a limit, it turns out to not be quite as important. Okay, we're going to look at one more. We can get these to scooch down. Oh dear, all sorts of stuff popping up. Okay, that disappeared. Let me see if I can grab it again. Okay, give me a second here. Okay, I've got everything fixed. So now let's look at our last one. Let's look at the limit. This will be D, I think. Limit as x approaches 1 of my function. So again, I look at the limit as x approaches 1 from my left, limit as x approaches 1 from my right, and then I compare those values. Well, here's 1 up here. X is 1, what is y? As I approach from the right, we can see that my limiting value is 3. As we approach from the left, I can't even approach it from this direction. I have to come in over here. You can see that my limiting value looks like it is 5. Now remember, it's a hollow point, but that's okay because it means it's getting close to and approaching but not equal. These are not equal, so the overall limit as x approaches 1 of f of x, d and e, does not exist. Okay, so when you're working through these, that's kind of the important thing to remember. The limiting value and the functional value don't have to be the same. In fact, when I'm working with these, a lot of times those hollow points, it might end up throwing you off. Don't worry about those. We just have to look at what it's approaching or getting close to, because that was the whole idea of a limit. Now we have a couple takeaways here that are very important. Let's see if I can scoot this where I need to. And the first big takeaway that we should probably consider is to be able to talk about a limiting value and a functional value. So what we end up with here is a function does not need to be defined at a point. So a function does not need to be defined at a point in order for the limit to exist at that point. Now we really saw some good examples of this in the graph above. And you'll be looking at a lot of other types of functions in your homework, but it's the same basic approach, especially with the piecewise graph. So as usual, if you have questions, send me a quick screenshot with your phone. You can take a picture of your work and text it to me, or you can also set up an appointment to meet online. I'll be talking about online office hours soon. We haven't got into that. You have your Pearson Connect so far, but I didn't want to overwhelm you with too many things, but we'll have some availability for online office hours coming up as well. Good luck, and please let me know if you have any questions.